section 2.3, page 2, where we're going to solve a series of derivatives. Now, keep in mind, here you're given the directions that you first should make sure that each function is written in the form of a constant times a variable to an exponent, and then you'll be taking the derivative. But generally, you're just given the second part of the directions, which is to find the derivative of the function. We'll go ahead and start with problem A. We recognize that x feels like it's in the base, but it's trapped inside of a radical. So the first thing we need to do is use our formula that says it will stay x to the fifth, but it will become a fractional exponent. And this is written so large, it may not look like an exponent here, but hopefully it does over here, where I'm still going to copy my exponent out front, and then I'm going to subtract 1 from the exponent. But because I have a fraction, don't forget that we need 1 in the disguised form of denominator over denominator, because fractions can only be subtracted if they have the same denominator. And now I can calculate 5 minus 7 to get negative 2. But we're going to want to get in the habit of answering without negative exponents. So this term needs to go to a denominator where you could think of x as being over 1. And so therefore we've left the top of that fraction blank and moved the x to the 2/7 to the denominator. So now we can multiply across the tops to get a 5. And multiplying across the denominator just really brings the terms together. Even though we started in radical format, you can go ahead and answer with fractional exponent format. Problem B. At first, hopefully you saw the question was really 9 over x, but remember, I can't have terms in the denominator. So I need to think of an invisible exponent becoming visible to be a 1, and then I need to move that up to the numerator, and so therefore the exponent becomes negative, and I don't need to write that this is over 1. Now it really just looks like a whole number, where I'm going to move that exponent out front with the 9, so that they can be multiplied together to give me negative 9. I'm going to subtract 1 from the existing exponent, and doesn't need to be changed as a fraction, but negative 1 minus 1 is negative 2. And again, I want to fix that negative exponent. I didn't have a denominator, but I can envision a denominator where the x squared moves to the denominator. Notice negative 9 did not. Technically, negative 9 has a positive 1 exponent, so it does not need to be moved. This was negative 9 times x to the negative 2, so only the portion with a negative exponent moves to the denominator. Example C. S of t, so t is our variable, and here's our variables in the denominator. Now remember, it's only the t that cannot be in the denominator. The 4 is okay there. So again, if I thought of t as having an invisible 1 exponent, I'm going to bring it up to the numerator by making that exponent negative. And this may be deceiving the way I wrote it, because you don't really see it in the numerator, the top. So if it makes more sense to physically write the t to the negative 1 on top of the 4, we don't need to write 1 times t to the negative 1, since 1 times anything is itself. But now what's going to happen is I'm going to think of having this coefficient of the fractional 1/4, where I'm going to bring, a negative 1 out. There is a mistake here, right? We're missing that negative 1. Then I'm going to subtract 1 to get my negative 2. And I need to bring that to the denominator. And so really this answer should be negative 1 over 4t squared. Next problem, D. So again, I'm thinking of the 5/11 as just really a coefficient, where I'm going to have my x cubed in a numerator, so it doesn't need to be moved. I can just think of the derivative of x cubed to be, bring the 3 out front, subtract 1 from the exponent, so that I have my 3x squared. And if I need to think of it as a fraction so that I can multiply my numerators and multiply my denominators, go ahead and write it over 1. But basically, we're going to have 15x squared in a numerator and 11. You generally don't want to write this as the mixed number 15/11 x to the 2 because a lot of people make it deceiving where the x squared should go. So making it clear in the numerator is your best bet. Notice there's a lot of similarities in these two problems. The only difference is instead of the x cubed being in the numerator, it's in the denominator. In that case, I do need to move it to the the numerator, and change the exponent to be negative. Or in my case, I just wrote it to the side with a negative exponent. I'm going to bring that -3 out front. I'm going to subtract 1 from the 3. And again, if I needed to think of it as a fraction, so I could visualize numerators and denominators, I can. Remember, we want to practice having variables with only positive exponents, so our negative exponent needs to move, in our case, to the denominator. So this term now has a positive 4 exponent, and as I multiply across the tops to get -15, and the denominators with an 11, x to the 4th, my -15 and 11 stay where they are because they both have invisible 1 exponents. Problem F. I've got 1 over the square root of x. We don't want x trapped in a radical. And remember, we can think of this as being you can't really see, that was a 2 in the indice and a 1 exponent. So using our formula of a over b, I'm going to have x to the 1/2, but it's in the denominator. So it needs to be brought to the numerator with a negative exponent. And then this -1/2 can be moved out front. It can have 1 subtracted from it. And as we've seen, if I have a fraction and I'm subtracting 1, we generally want the disguised form of 1 to be denominator over denominator so that my denominators match, and -1 minus 2 is -3. So here is my derivative, but I'm going to fix that negative exponent by bringing x to the 3/2 to my existing denominator of 2 for -1 over the fraction as the top of the fraction 2x to the 3/2. And again, notice I've been using the derivative notation on all of these.